so we can have some calculations of the ratio of the rock mass strength to the in situ stresses. So before describing this chart and give you an example of how this works, just quick reference of where this chart was based. So these 62 tunnels are bore tunnels, and the span of this tunnel is about 12 meters. They were constructed with a conventional method, opened by a top heading and bench. And the cross section of these tunnels is about 80 to 120 square meters, and the overburden is up to 600 meters. So this is the experience that this chart was based. It was we were very lucky because this highway crossed perpendicularly, almost perpendicularly, almost all our geotectonic units. So we have a great variety of rocks and conditions, and overburden, and in situ conditions, groundwater conditions, in tectonic zones. So we had a lot of range of geological conditions to explore. A nice photo from this conventional tunneling with the top heading and bench method. Now, this chart, before giving you an example of how it works, you can find in the columns the rock mass structure based in the GSI system from the latest development of Hook and Marinus in 2000. This is the structure from the basic chart. And we have two sets of columns. The two left columns are small overburden, and the two right columns are large overburden. So where we're talking about small and large overburden, here the limits are given between these sets of columns. So from the first two rows of structures, we have an overburden limit of 150 meters. Then in the very blocky, the limit is around 100 meters. And then in the three last rows, the overburden limit may be around 70 meters. Again, I have to highlight here that this is a chart that gives you, urges you to think about how the ground behaves without just giving a numerical sum of some parameters and just to rely on this sum, on this rating to give you and analyze from a numerical modeling to provide you the support measures. So this is, in general, some rough but very well allied examples of how we can shift from one tunnel behavior to another when the rock mass structure changes, when the overburden changes, and now according to the intact rock strength, which it's the maximum strength that a rock mass can have, but then is reduced through the Hooke-Brown criterion with the GSI. So we have a low sigma CI and a high sigma CI. This low and high may be around 50 to 20. Of course, this is again experience from these 62 tunnels in this very wide range of situations. So if we have an example of heavily fractured rock mass, let's say an RQG of up to 20%, 0 to 20, and a limestone with a sigma CI with a UCS, uniaxial comprehensive strength, was about 60 megapascal, and a tunnel under a 50-meter cover, then we will have a disintegrated rock mass. So we will be in a poorly interlocked, heavily broken rock mass with mixture of angular and rounded rock bases. We will have low overburden and a high intact rock strength. So we will lie in the case of 18 box. Raveling ground we will have under these conditions. So the support measures should be based in this behavior. Let's see an example of 4 ground types an example of how this methodology works from the ground type to the support system based on these behavior types. So the first step is to define the ground types. So here we have in this example, we have an undisturbed to moderately disturbed thick to medium thickness sandstone beds with sporadic thin films of siltstone. So we have not a very disturbed rock mass, high GSIs, 50 to 60s. Here GSI is just, let's say, is used for the classification and not as a number for the calculation of anything. We will see that towards the next steps if we use some values for the analysis and numerical analysis of the tunnel support. Of the ground type 2, we have the moderately disturbed with medium thickness sandstone beds with thin films of siltstone. So here we have something which is more deformed, more broken, and again, sandstone prevails. We have heterogeneity, but it's small. We have only thin films of siltstone here, which does not reduce a lot of the rock mass strength, not at all. The ground type 3, we have a folded here rock mass, so the rock mass is strongly disturbed, a folded rock mass that retains, of course, its structure with sandstone beds, again dominating the siltstone ones, 80% sandstones to 20% of siltstones. And the last ground type is ground type 4, where we have tectonically deformed, intensely folded siltstone with broken and deformed sandstone layers, forming an almost chaotic structure. Always we have some values of GSI next to them, but just here we need to define these ground types if we want to use any other system just to classify, just to describe the rock mass, we can do that. Here just we can use the GSI for the heterogeneous rock masses such as fleece. So we can use this chart here. You can see projected the ground types we discussed before. And we can proceed now to finding this, defining all these ground types with the key parameters. The key parameters of lithology, the UCS of the intact rock, the GSI or any other system used, the distance of discontinuities, friction of these discontinuities, JRC, the persistence of the discontinuities, anything that will dictate the behavior of the rock mass. And then we can determine the parameters either from the Mork-Loeb failure enveloped using the Hook and Brown and the rock data sets from rock science. Here the example is a maximum overburden of 35 meters, so we can find the equivalent friction angle and cohesion of these rock masses. But we will use these rock mass properties if the rock mass behaves isotropically. If this does not behave isotropically, then we have to use other parameters of the discontinuities if it is gravity-driven failures. So using this tunnel behavior chart in this design, you can see that the ground type 1 lies in the case of a blocky rock mass and small overburden with high UCS, so we are in number 6 in our projection. And ground type 2, it's a very blocky rock mass, so we may have again some wedge failures, but we can also have some chimney type failures in these rock masses. In the ground type 3, due to a wide range of the UCS, we may lie to the case of 13 or 14, which is a chimney type with wedge failures. If we have some low UCS there, we may also have some small shear failures along the tunnel perimeter, but mainly the problem is dictated by crown failure, so chimney type overbreaks and some wedge problems. In the ground type 4, here we have some stress-induced problems, So we have to analyze either it is squeezing or shear